Welcome to the webinar series of SAR data processing. In today's webinar, we will see the SAR data processing aspects as a part 2. In the last webinar, we have seen the SAR data processing in which we have seen the algorithms of SAR raw data processing. In that webinar, we have seen how the raw data is converted to the processed data using the signal processing algorithms. In that webinar, we have seen the concepts of the pulse compression techniques and synthetic array approach. From that algorithms, we have converted the raw data to the processed data using the range Doppler algorithm, which mainly uses the range compression, azimuth compression, and the range cell migration correction algorithms. In today's webinar, we will see the geometrical corrections of level 1 data, which has been converted from the level 0 data. So what are the different SAR data products? The different SAR data products are the raw data products, which is the signal level data. After that, there are slant range products, which includes the single loop complex product and single loop detected product. After that, after the data processing, we can obtain the ground range product and then the geocoded products. The geo products are two types: the geocoded ellipsoid corrected product, which is called the GEC product, and the geocoded terrain corrected product, which is called the GTC product. So this is the entire chain of the SAR data processing. So if the SAR raw data is available, then we can apply the signal processing algorithms and the algorithm like range Doppler algorithm to focus the raw data to the single loop complex data. So this is called the level 1 data and this is called the level 0 data. So after we will get the level 1 data, we can do the post processing to have the ground range product, geocoded ellipsoid corrected product, and geocoded terrain corrected product. So we have the different level of products and we can have the different level of data processing. In the last webinar, we have seen the signal processing aspect in which we have converted the raw data to the single loop complex data. In today's webinar, we will see how to generate the ground range product, geocoded ellipsoid corrected product, and geocoded terrain corrected product. So what are the SAR geometry parameters? So after we have got the level 1 data, so we have to do some of the geometrical corrections to the level 1 data to have the ground range data and geocoded ellipsoid corrected and geocoded terrain corrected data. So this is a typical SAR geometrical parameter diagram. Okay, so if A is the radar platform and B is the flight direction, so in this direction the SAR is moving, and C is the nadir point, and this is the C is the nadir point which is just perpendicular to the SAR platform. D is the azimuth. So this is the direction in which the SAR is moving and the image is moving is making. So this direction is called the azimuth direction. E is the range and this direction is called the range direction. So this is the radar beam. So this beam is towards the SAR is called the swath or the range, and this direction is called the azimuth direction. Then this total distance is called the imaging swath. And G is called the far range. This G is called the far range and H is called the near range. So this is a near range, this is a far range, this distance is called the swath, and this direction is called the range direction. I is the slant range. So this direction which is in the slant plane, so this is the slant range. J is the radar beam width. So this is the what is the beam? It is illuminating the Earth surface. Then this J is called the radar beam width. And L is the energy pulses. So this blue curves are called the that the energy pulses, means what are the electromagnetic wave it is transmitting. So these are the energy pulses, M are the echoes. So these are the transmitting, and after the backscatter, M is the backscatter pulse, or we can say echoes. Theta is the incident angle. So what is the incident angle? Which is the radar beam is making with the normal to the plane. So this is the our surface, and this is perpendicular to the surface. And what the radar is making the angle, this is called the incident angle. So this is called the incident angle, and this alpha is called the depression angle. This is a horizon, means which is parallel to this surface. So this is called the horizon, and this radar beam is making with the horizon is called the depression angle. So this is a depression angle, and this is the incident angle, and this is the look angle, which the radar beam is making with the nadir point. So beta is the look angle. So this is the look angle, this is the incident angle, and this is the depression angle. So the for the flat surface, this look angle is equals to the incident angle for the flat surface. But the surface is not flat, then they are not equal. So what are the slant range product? So SAR can image both in ascending node and descending node. SAR can look in both directions, means the right directions and the left direction. So it has two looks. It can be look in the left way or the right way. So due to this imaging geometry, because SAR can image in both the ascending and descending node, and it can look in both the look right and left look. So the slant range image can be flipped in the range direction or azimuth directions or both the direction. So these slant range products are geometrically not corrected. Okay. So this is this is the diagram for the ascending and descending node. Descending means if satellite goes from north to south. So this is the descending node, and ascending node when south to north, that is called the ascending node. So because SAR is an active sensor, so it can image both in ascending and descending node. But the most of the optical sensors which uses the sun as a source of energy, it can image only in the descending node, and also it can see in either one of the direction. But the SAR has capability of looking both the direction, either left or right, and both ascending and descending node. Due to this, we have lot of geometrical distortions in the image. So if this is the earth surface, means original surface, actual earth surface, and this is range and azimuth direction. So if the SAR will acquire this data, means in the all the possible combination, means right, like ascending right, ascending left, and descending right. Means ascending node right look, ascending node left look, descending node left look, and descending node right look. Okay, so four possibility combinations are there. So the same image can be acquired at four different ways in four different geometries. Okay, so if you can see, this is the actual surface, and we have the combination of ascending right, means if the direction is this way, ascending from north to south, and it is looking right way. So direction is this and looking in this direction. So this image, how it will happen means, and the satellite is moving ascending and looking in the right way. So this data will be right first. Okay, so you can see the azimuth will be flipped. Okay, so you can see the flip in the azimuth direction. So this data will be looked in the slant range plane like this. Okay, so another case will be ascending left, means the SAR is moving in the north to south, and it is the look is the left, so it is looking from this direction. So in this image, if it is moving this one and looking this direction, so how the data will look like, means this is written first. So first this data will write. So this is the data, it will come first. Okay, so this is the some geometrical changes in the images. And another case is descending left. In the descending left, the image is not no change in the image. So no flip in the range and azimuth direction. So there will be no flip. In the descending right combination, we have the range flip. Okay, so means descending right means the direction is this way and it is showing this way. So this direction will be flipped. So this data will be written first. Okay, so this is the some of the geometrical changes in the images due to the different geometry of viewing of the SAR sensor. So what are the properties of the slant range product? The pixel direction is range and the scan direction is azimuth. SAR slant range process products can be obtained in two ways, like SLC, single look complex, or the detected product. So in the SLC image, it will contain two images, real and imaginary. And in the detected, we can convert either in the amplitude or in the intensity images. In the amplitude, just we have to have the formula of under root of real square plus imaginary square, and they are geotagged, means the lat long positions are attached to the pixels. Okay, so what is the range pixel size? It is given by C by 2fs. So fs is the sampling frequency, then the pixel size is C by 2fs. So that is not square pixel size. So we have different range pixel size and different azimuth pixel size. The azimuth pixel size is given by the Vg into Pri. Vg is the ground velocity of the sensor and Pri is the pulse repetition interval. So range pixel size is given by the C by 2fs and azimuth pixel size is given by the Vg into Pri for the strip mode SAR. So the range pixel size same and azimuth pixel size changes with modes. Okay, so this C by 2fs will be same for every mode, means either the it is for the strip mode, scan SAR or spotlight. So this range pixel size will be same, but azimuth pixel size will be different modes, will be different. Means for the strip mode it is Vg into Pri, and for other mode it will be different, like scan SAR and the spotlight mode, the azimuth pixel size will the formula will be different. So how the slant range product will look? So this is the raw data, means it is the one of the component, real part of the raw data. Then after doing the signal processing, we will get the slant range product like this one. So this is the unfocused data and this is the focused slant range detected product, but it is not geometrical corrected. Okay, so this is the SLC product, means if we are getting the two files, as one is real and second is imaginary, so this is called the SLC product. In the SLC we have two files, real and imaginary. So if we apply this formula, amplitude is equals to real square plus imaginary square, then we will get the detected product. So this is our single look detected image. Okay, then this is the single look complex image. So now the slant range is not geometrically corrected. So what we have to do, we have to project the slant range to the ground range. Okay, so this is the slant range. Okay, so slant range is the straight line distance between SAR and the object. So this is called the slant range. On this plane is called the slant plane, and this range is called the ground range. The ground range is the horizontal distance between the SAR object, SAR and the object. So this is called the ground range. So our that processing and everything in the level 0 data processing will be done in the slant range plane. Okay, so that single look complex image or single look detected product we will get as a slant plane. Okay, so the pixel size is C by 2fs, but it is not geometrically corrected. So to do the geometrical corrections, we have to project the image to the ground range plane. Okay, the slant pixel size is C by 2fs. The ground pixel size from the geometry we will get C by 2fs and into the sine of incidence angle. Okay, so this is the ground pixel size. So this is uniform pixel size. So we have to do the uniform spacing in the ground range product. Okay, so you can see from this geometry also, this is the look angle, this is the nadir. So this is called the slant range, this is slant range, and this is called the ground range, and this is the gamma is the look angle. So we can find this ground range by using the trigonometry, which is given by the formula the C by 2fs sine incident angle. Okay, then slant pixel size is given by the C by 2fs. So the SAR can be represented either in the slant or ground range. So in the processing, what we are doing, we are processing in the slant range plane, and after doing some of the data processing, we can project the image to the ground range plane. So the slant range is the natural SAR range observation coordinate defined as a line of sight from the SAR to each reflecting object. Ground range is the slant range projected onto the earth. Slant range data can be converted to the ground range by resampling. So if this is the slant range, in the level, after the level 0 processing, we are getting the level 1 product. Then we will use this formula of converting the slant range to the ground range, and we can convert to the slant range product to the ground range product by using this formula and by resampling. Resampling means we can do the interpolation like CC interpolation and NN interpolation. So the imaging geometry is in the ground range for the ground range product. The square pixel size. So in the ground range product, both range and azimuth pixel size should be same. So we have the square pixel size. In the slant range plane, we are not having the square pixel size because the range pixel size is not equal to the azimuth pixel size. And the ground pixel size is given by C by 2fs sine of incidence angle. And this product is also the geotag, means lat long is provided in these products also. So you can see this is the slant range plane image and this is the ground range. So this is, you can see some compression in the image. So slant range product, we have some of the geometrical distortions, means some of the compression in the image. But in the ground range product, we have the proper geometry. So from the formula of the conversion, we have changed the pixel size. So we are using the C by 2fs sine incidence angle to project the slant range to the ground range. So what are the difference between the slant range and the ground range? There is a scale difference in the slant range and ground range images. Ground range resolution is better at the far range, unlike the optical sensor. Okay, so in the optical sensor, as we go towards the far range, then the resolution is decreasing. But in our SAR, the ground resolution is better at the far range due to the formula of sine theta. The differences between slant and ground range resolution are highest at a small incident angle. So if we will use the small incident angle, means like we are using 20°, 30° or 15° incidence angle, then there is a very much variation between the slant range and ground range images. So we can have the more geometrical distortions in the slant range images if the look angle is very small. But if the look angle is high, then we have the little difference between the slant and ground range images. So after that, means after converting the slant range and the ground range, the basically that image has no lat long, or we have not projected to the ground, means it is not oriented towards the north. So it is a simple rectangular images, but having the only the geo information, lat long information, but we have not rotated the images for towards the map geometry. So for that we have to do the find the lat long of each pixel. So that lat long of each pixel is founded by the SAR geolocation algorithm. So what is the SAR geolocation algorithm? Geolocation is the calculation of the geographic coordinates of a image pixel. Radar measures the range from the sensor to the target. Okay, so normal radar, it will measure the range from sensor to target, but the synthetic aperture additionally measures the Doppler history of the returns from the target. So the SAR, it will also measure the Doppler history. As I have told in my previous webinar, like it calculates the Doppler. So this makes it possible to construct a rigorous sensor model to geolocate the pixel position on Earth. Okay, so means if we want to find the lat long of any pixel, then we have to form one range equation, one Doppler equation. Okay, so from this range and Doppler equation, we can geolocate any pixel of an image. So in our SAR, we are not using any roll, pitch, and yaw information for the SAR geolocation, because it is estimated through the Doppler, because we are estimating the Doppler from the images. So that Doppler can be used to estimate the roll, pitch, yaw from angles and through the Doppler equations directly. Okay, the accurate Doppler is estimated from the image needed for SAR image focusing. Okay, so if we are doing the SAR signal processing, so we have to estimate the accurate Doppler. So that accurate Doppler will give the accurate attitudes. So if the Doppler is not accurate, then the SAR image is not able to form, or it will be defocused. Okay, so after using the proper Doppler, we can have the proper SAR image and using that Doppler for our geolocation algorithm. So attitude information essential for the optical sensor geolocation, and optical geolocation accuracy depends on the attitude accuracy. So mainly for the optical sensors, attitude information are needed. So and the optical geolocation accuracy mainly depend upon the roll, pitch, yaw accuracy. What are the sense? What is the accuracy of our IMU? Means what is the roll, pitch accuracy of the optical sensor? But in SAR, we are not dependent on the accuracy of the roll, pitch, yaw while geolocating a SAR pixel. Okay, we are just using the range and Doppler equation to geolocate the target, and the Doppler is estimated through the image itself. So what is the geolocation? So geolocation is the process of calculation of the geographic coordinates or latitude and longitude of a image pixel. So if this is the slant range image, so any pixel, so that pixel, if you want to the lat long, so how to find that lat long? Through the SAR geolocation and technique. So what is the model for the SAR geolocation? So model, it has the Earth surface and the SAR Doppler equation and the SAR range equation defining the distance from range to the target. So if this is the sensor, means in the airborne platform, so this is called the sphere of the constant range. So this range equation will give one sphere equation. Okay, and this Doppler equation will give one cone equation. Okay, so this is the cone and this is the Doppler, and it will intersect with the Earth surface. Then the intersection of these three will give the geolocation of a point. So we can geolocate one target. Okay. So what is the range? Range is the slant range distance from the SAR sensor to the target. So how the range is given is if this is the satellite, and it in the axis ys and zs is the position of the satellite, and xt, yt, and zt is the position of the image pixel. Then we have to determine this. This is unknown, xt, yt, and zt. But we know the range. So first equation is the range is equals to this. So in this equation, r and xs, ys, zs are known, but xt, yt, zt is unknown. So first, this is the range equation. Second is the Doppler. What is Doppler? When an observer or the source moves with respect to the source or observer from a waves, a shift in frequency is observed. Okay, so this is called the Doppler. So in this video, we can see how the Doppler cone is forming. Okay, so this is the Doppler equation. And what is the Doppler? As I already told, when an observer moves with respect to the source, then there is a shift in frequency. That shift in frequency is called the Doppler frequency. And for the SAR case, after simplifying this equation, we are getting the equation at 2v. V is the satellite velocity, and this is the squint angle and lambda. So this is the Doppler shift in the SAR image. Okay, so this Doppler what we are getting, because SAR is moving with respect to the Earth surface, so there is a relative motion between the source and the observer. There is a source is the SAR sensor, and the observer is our image, means Earth surface. Okay, so due to the relative motion between the SAR and the target, means target means the Earth is also moving. So there is some relative motion between the SAR and the target, and there is a Doppler shift between this, means frequency shift between this SAR and the Earth surface target. So that shift is given by this equation. So we have two equations. One is range equation, second is the Doppler equation. So for a particular image cell, we have two information. One is the range information, means we are getting the range formula, and we are getting the Doppler angle. Doppler angle means what is the cone angle. As I told, this it will form the Doppler cone. Okay, so this angle is called the cone angle in the Doppler cone. So we have the range, we have the Doppler angle, and we have the amplitude. Means what is the energy, scatter energy in the image. So for a particular pixel, we have three information: range information, Doppler information, and what is the backscattered energy, which is converted to the DN values as 173. So if this is a SAR and this is a SAR image, so for any point we have this range and this Doppler angle. So there is a relationship between this Doppler cone and the squint also. That is the squint angle is the 90 minus the Doppler angle. As in the previous lecture, I have told the squint is the angle made by the radar beam with respect to the zero Doppler plane. Zero Doppler plane means where the Doppler is zero, means the relative motion between the sensor and the Earth target is zero. That plane is called the zero Doppler plane, and our the SAR processing is done in the zero Doppler plane, and the angle made by the radar beam with respect to the zero Doppler plane is called the squint angle. Then the squint angle is also given by 90 minus Doppler angle. Okay, if squint is zero, then we have the zero Doppler plane, or squint 3, it form a Doppler angle of 87 degree. Okay. So this is a relationship between the Doppler cone angle and the squint angle. So we have the geometry of the SAR geolocation. If this is a SAR platform, so what it will form from the range equation, it will form the these circles, means this is the concentric circles formed by the range equation, and this equation is called the hyperbolas. Means from the Doppler equation, that is a normal cone, when it intersect with the Earth surface. Means this is the Earth surface. When the sphere is intersect with the Earth surface, means it is intersected by the plane, then it will form the circles. So after intersection with the Earth surface, that range equation which is representing the sphere, then after that intersection it will form a concentric circles, and our Doppler will form a equation of the hyperbolas. So this is the hyperbolas. Okay, and this is our illuminated surface. So what we have to do, we have to find the intersection of these concentric circles with the hyperbolas with the Earth surface. Okay, so we have three equations and three variables, means x, y, z, our three variables and three equations. From that we have to form the equation, and we have to solve, and we have to find the x, y, z. So what is the SAR geolocation? We have this Earth model, means this is the Earth model equation. So we have studied that we have using the like ellipsoid equation. So this RE and RP will form the ellipsoidal equation. Generally, what we will follow, WGS 84 ellipsoid. So this surface, Earth surface is ellipsoid. So we are considering the Earth surface as WGS 84. Then this RE and RP are predefined. So we will insert this RE and RP in this ellipsoidal equation. And this is the range equation, and this is the Doppler equation. After solving and converting to the converting into the Cartesian coordinate, this is the SAR Doppler equation. So these are the three equations. We have to solve these three equations, and we have to find the x, y, z. This is the unknown x, y, z of the point. So if this is a SAR sensor, and this is the range, and this is the x, y, z, and if we will form this equation, and after solving, because this is a non-linear equation, so we will use the Newton-Raphson method for solving. It is an iterative method to solve this equation. After solving this equation, we can find the x, y, and z. Okay, so all this information is given in the SAR data. Means apart from the image, we will get the orbital epiphenomena, which is called the state factors, which contains the time, x, y, z, and the velocity vector. Okay, so from this information, we can form and we can geolocate any target pixel in a SAR image. So in the previous slide, what we have seen, it is the non-linear equation and it has the degree of 2, means after solving we have two solution, means x square, then we have the two solution. So for this one, how to find the now one of the solution which is the correct solution, that is ambiguity is solved by the right or left look prior information, because we know what is the look direction, because from the SAR parameter file we know the SAR is looking either left or right. So that information is used to solve the which is the correct solution, because after solving this equation we have two solutions. So which is the correct solution, we will decide on the basis of the formula of like it is the left loop or the right loop SAR sensor. Accordingly we will choose the solution. Okay, so basically there is two type of SAR geolocation. One is set like image to ground geolocation, and second is called the ground to image geolocation. So what is image to ground geolocation? Means for a given scan pixel index, means in the image we have the scan and pixel index ij in the slant range image. Okay, so for that we are calculating the lat long. So what is that? For particular ij we are calculating the lat long. So this is called the forward geolocation. Okay, so now what is the ground to image geolocation? It is called the backward geolocation. So for given lat long in the geographical plane, input scan pixel index ij in the slant range image is computing using the Ronch-Doppler geolocation algorithm. So it is the backward, means for a particular lat long in the geographical earth surface. What is the ij? Means from where the SAR image pixel is coming from. Means if we have a particular geographical plane, means if we will take a dam, if we have the dam, means we have for that x y z, means we have the lat long position and z value. So that value we know for particular dam. So for that particular geographical position, what is the image location for the SAR image? So that is called the inverse, or it is called the backward geolocation. For a particular lat long position, we have to find the ij position in the image itself. Okay, so this is the forward, means for a particular ij what is the lat long, and for the backward geolocation for a particular lat long what is the ij. Okay, so for our geometrical transformation or geometrical correction, we are using these two algorithms for the geometrical correction or geolocation of any target pixel in a image. So what is the difference between the optical and SAR geometry? Okay, so if you can see, this is a SAR antenna and this is the our optical lens. Okay, this is the optical lens and this is the what is the imaging plane or a focal plane of a optical sensor. So since it is a side looking, so this geometry of the SAR antenna is like this. If A, B and C are three targets. Okay, so if the SAR will see in this side looking geometry mode, then this A, B, C will image in the slant range plane like A dash, B dash and C dash. So this is called the slant range geometry of the SAR. So A will right here, B right here and C right here in the slant range plane. But in our optical sensor, how it will be right? Using this lens and using the like mirror formula, this is projected here, B is projected here and C will projected here. So this is basically the difference between the SAR geometry and optical geometry. So we can see here the transformation is basically the non-linear here, because sine theta component is adding. So this is the transformation is non-linear in the SAR image. But if we are not considering the terrain surface and simple this formula only, so we can say this is the basically linear nature. So this is simply linear. So we are using the collinearity equations in our in our optical sensor. So there is the linearity between the imaging plane, but here is the non-linearity. So in the optical, linear ABC from A dash, double dash, B double dash and C double dash. Okay, so here non-linear concept is there, there in the optical linear concept is there. So if this is the optical geometry means this is the CCD array, means it is a charge coupled device, and we have to geolocate this one. This is the optical system, means this is the CCD array, and it is the lens, and it will project into the this surface, and this is the how the ground range resolution will form from the formula. So this is the images for a particular CCD pixel, and as it moves in the azimuth direction, it will form a rectangular image. So this is the optical geometry, and this is the equation which is used for the collinearity equation for the optical geometry. But for the SAR geometry, we are using the range Doppler equation. So this is the range equation, this is the Doppler equation. So after third equation, also we will use Earth surface for the intersection of these two equations. So we can say there is a basic difference between the SAR and optical SAR geometry and the SAR and optical geolocation process. Okay. So in our process, we can see in the SAR geocoding, we have two processes. One is the geocoded ellipsoid corrections, which is called the GEC. What it will consider, the Earth surface in the GEC correction is considered as a smooth ellipsoidal surface. So what Earth surface is considered as a smooth ellipsoidal, useful for the areas where surface is flat or dams are not available. Okay. So for our geocoded ellipsoid correction is done for the surfaces which are normally flat or the dams are not available. In the geocoded terrain corrected terrain correction products, or it can be also called as the ortho rectification. So it generates the precision corrected products by the use of digital elevation model. So what is the digital elevation model? Means it will contain the Z values of the terrain. So for the geocoded terrain corrected products, we are using the DAM to correct the geometry of the SAR images. Okay, so these ortho-rectified or geocoded terrain corrected products can be overlaid with other remote sensing images. Means if we have any other optical image, any multispectral or hyperspectral, then the geometrical accuracy will match with that remote sensing image, and they will exactly overlay between the different images. So what is the why it is, and we have to do the SAR geocoding, because our slant range products are not geometrically corrected. Means it is neither in the proper orientation nor in the proper scale. So we have to do some of the geometrical corrections. So first we have to do the SAR geolocation. For the SAR geolocation, what we have to find, for every pixel we have to geolocate the image pixel and find the lat long. Once we are get the lat long, and we know the what is the terrain surface, from that terrain surface what we will extract the dam from there. So if we are using the dam, then we will use that dam and our geolocation process to correct the image. Okay. If the dam is not available, then we will take the average height of that imaging surface, and that will be used for the geocoded ellipsoid correction. So what are the algorithms what we are using? So basically there are two algorithms. One is the geolocation grid algorithm, and another is the range Doppler or rigorous sensor model algorithm. So basically these two type of algorithm we can use for our geometrical correction. So GEC is used for the average height. Means in the GEC correction we will use the average height of the image surface. And for the GTC, we will mean geocoded terrain correction, we will use the dam of an imaging surface. So what is the SAR geocoding? Means if this is the input surface, okay, this is a range Doppler geometry, means it is in the slant range geometry, means in which the range direction and the azimuth direction is given. So what it will do, we have to find and this equation, and this is the slant range image, and we will have the one ground image. Okay, so this is called the reverse geolocation. Okay, so if we have the output space, means if we have the output space, say we have any dam. So for a particular pixel, we already have the lat long and height value. Okay, so for that particular lat long and height, we will do the reverse geolocation. Means for a particular lat long height, we will go the reverse geolocation. We will extract the IJ from where, from the image it will coming from. So that ij value we will find out, and using the resampling we are putting back to the this in this pixel value. So in this way we are doing the geocoding part. Means for a particular lat long we are finding the ij, and for that ij what is the dn value, that dn value we are filling here. So this is called the reverse geolocation or the backward geolocation. Okay, so that is used for filling the image pixels in the geographical plane. In this way we will correct the we will correct the slant range images, and we will convert to either in the GC product or the GTC product. So for the geocoded ellipsoid correction using the geolocation grid, how to be done? First, from the generation of the latitude and longitude for each range and azimuth or pixel scan using the forward geolocation at each interval, assuming the average height. Okay, so for GEC, what we will do, for at every constant interval, we will find for particular ij what are the lat long. So we will form one geolocation grid. In that geolocation grid, what we will have for a particular ij, what is the lat long. So particular ij we have the lat long. So in the output space, what we will do, for the corresponding scan pixel in the input space, slant range image is computing using the polynomial fitting. Okay, so from that way, means in the output space, what we will do, for the corresponding scan pixel in the input space is computing using the polynomial fitting. So for every grid we have the lat long and ij, we will fit a polynomial, and using that polynomial to find the dn value for a particular pixel in the image. Okay, so this is the geocoded ellipsoid correction using the geolocation grid. So how the image will be look like? So this is the slant range image. So here the geometry is not correct because it has compressed and it is not properly oriented. So I have already showed the four possible combination. So after the that geometrical correction or geocoded product using the average height, we are correcting this image. So you can see this is the properly oriented towards the earth surface, and this you can see these features or mountains are coming in this direction. Okay, so this correction will do automatically, means that flipping of range azimuth we don't have to do manually because we know the lat long. Then it will automatically go to the map geometry with the help of the equations, and because we have range Doppler equation and we have to solve that equation, and we have to do the transformation using the geolocation grid, and that will automatically do everything using the constant height of the terrain. So this is the slant range image and this is the geocoded image. Okay, so this you can see these mountains are coming here. Okay, so this is the GEC, means we are using the constant average height here. So this is another product, GEC product. This is a geocoded product grabbed on the dam. So you can see this is some of the that layover and foreshortening which I have explained in my first lecture, basic concepts of the SAR remote sensing, layover, shadow. Now in the geocoded ellipsoid correction we are mainly using the average height, but because SAR is a ranging sensor, so it has very much relief displacement and very much geometrical distortions due to the height of the terrain. Okay, so we have to correct it. If the terrain is undulating or it is containing more height, then we have to use the digital elevation model or dam to correct the SAR images, because it have great relief displacement as compared to the optical sensor. Okay, so how the topographic displacement for optical sensor and SAR sensor? The displacement is given by the h tan theta for the optical, and displacement is given by the h cot theta for the SAR, where theta is the look angle. Okay, so due to the different imaging geometries of SAR and optical system, topographic displacement differ between the system. So horizontal displacement for the SAR sensor is highest near the nadir and decreases with the incident angle. Horizontal displacement can be severe at the small incident angles. Okay, So what is the layover or the relief displacement? So if this is the height, if this is h is the height, then this delta g l is the layover. Then this formula is given by the h cot theta. This formula is given by the h cot theta. Okay, what is the displacement or layover of this one? Because what is will happen? This is the ranging instrument. So this range, because it is a ranging instrument, this range will be shorter than this range. So it will return here. Okay, so this is the called the layover. So if we can compute the relief displacement for optical and SAR, we can see from the formula of SAR from h cot theta, if we have different look angles like 10 degree to the 85 degrees, so we can find out the height for if height of the terrain is 100 meter, then 100 meter will correspond to 500, around 500 meter for the look angle of 10 degree. So we can see for the lower look angle, the relief displacement is very much high. For a 10 degree and 100 meter terrain surface, the distortion is for of around 500 meter. But for the optical sensor, it is very much less, because due to the capabilities is it can image from 0 to 45 degree only. So maximum it can have only the 100 meter displacement. Okay, but in the SAR, it has the maximum of 560 meter, and lesser it will go towards the far range. Okay, so the low look angle have more geometrical distortion in the SAR images. If we want to image any surface and we are looking the low look angle, then the geometrical distortion will be high for the SAR imaging sensors. So we have three concept of layover, foreshortening, and shadow. So for geometrical distortions, so if you can see, if this is a terrain, so layover is the AB and AB dash. Okay, so what is the layover? Means if this is the point, A and B point are there, then it will image reverse. Okay, so B dash and A dash. Okay, but in the foreshortening, it will be compressed. Okay, so this CD you can see, it will have the C dash and D dash, means the image, there is a compression of the image. Okay, for the foreshortening. So this also I have explained in my last lecture, layover, shadow, and foreshortening. So shadow, where we have not got any energy. So this is DE represent the shadow part. So we have no energy in this part. So we have this layover effect here, said that foreshortening effect here, and shadow effect in this way. So this way are the three basic geometrical distortions of the SAR image. So how this layover and shadow will behave as we go from near range to far range. So from there, what we'll have, the layover will be higher in the low look angles. Okay, so from low look angle means towards the near range. As we go towards the far range, so layover will decrease, and in the far range, the foreshortening will happen. Okay, so we can see the top and bottom means it will right, top here and bottom here, means first top will be right and bottom will be right of any mountain. So reversal of that mountain means top will return first and bottom. So this process will goes to the uh, decreasing trend as we go from the near range to the far range. So we can see that layover will decrease, and here also it is decreasing. And after reaching the far range, we are seeing like it is converting to the foreshortening. Now bottom and top is same return, but with the compressed length. Okay, so this is called the foreshortening. Okay, so this is the way how the layover and foreshortening will behave as we go from the near range to the far range. Means as we go from the near range to the far range, the layover will decrease. From near to far means in the near the layover will be higher, and in the far range it will be the lower, and in foreshortening will be higher in the far range. Okay, so this is the typical example how the layover will look like. Like this is, you can see the hilltop. So you can see due to the layover, this it should be properly imaged to this position. If it is properly geometrical corrected, then it should be imaged here. But due to the layover, it is imaged, and you can see this hilltop is displaced from its correct position. Okay, so in our geocoded terrain correction, what we will do, we have the dam information. Means we have know the that height values. For that height, particular height, we will find the proper position of this hilltop, and we will displace this position to this position with the help of the digital elevation model. So what is the digital geocode terrain correction? This algorithm solves the range Doppler equation to determine the range and azimuth position corresponding to the position Px, Py, Pz on the Earth. It uses the backward geolocation algorithm, DAM for terrain correction. DAM is used to extract the actual height of the terrain and used to correct the layer and foreshortening effect geometrically. Okay, only geometrically it is placing the pixel position. Means it will not form the exact value, but just it will displays the values of the pixels to the correct positions. Means how it will do, it is use the geolocation algorithm, backward geolocation algorithm. Means if we have the particular dam, so for the particular dam we have the xyz values of particular dam. So for that particular xyz, we will solve the range Doppler equation. So for particular that one, we have the range equation and Doppler equation, and for that lat long, what is the ij values. Okay, so we have to calculate what is the pixel values of the SAR. So solving that range Doppler equation, we will find the ij value of the SAR image. So that ij value we will fill in that position. Okay, so that is called the backward geolocation algorithm, in which we are using the lat long to ij conversion. Okay, so using the dam values, because we have also one dimension in the z direction. So that dam z values is used for that ortho rectification, means for the correction of that layer and for shortening of the images. So how that geocoded terrain correction algorithm will look like. So if this is the slant range image, so what we have used the range Doppler equation and we have used the dam. So this is the GTC product. Okay, so you can see the correction of the layer and shadow. So this is stretching of this white values you can see. So this is the terrain corrected product. So if you have, we will drag this image to the dam. So this is the 3D view of the image. Okay, so this is the GTC product laid over the dam. So here you can also see this is the one of the product, and so you can see this is the stretching of the layover values. So if you are seeing this type of product, then you can see this type of effect in the GTC product. So you can see the how these two images. So this is the GEC product. So you can see the layover is here only. It is not corrected, but in the GTC it is corrected. So this is the this pixel value. It is keep on. We are writing this to the correct positions. So this it is forming like this one. Okay, so it is now looking like a proper mountain with this correction. Okay, so here you can see this one of the this hilltop, which is the GEC product. We are using simple average height for that image. So you can see that top position is displaced from this position. Okay, so we are using the image grabbed over the tab. So this position is not coming to the correct position. Okay, so after the GTC, we can use we can see how this this hilltop is goes to the correct position. Okay, so if we can see this is forming a it correct mountain. So this is Mount Fuji in Japan. Okay, so you can see the proper volcano of this shape in the ortho image of the SAR image. But here in the GEC, because we are using the average height to correct, this correction is not done. So that is the basic difference between the ellipsoid correction and the terrain correction. So you can see the full image of this geocoded terrain correction. So you can see the one, this it is the video of the correction, geocoded terrain correction of that image. Here you can see, and everything is done properly using the dam. Uh, so you can see as a real image type of thing after creating in and wrapping over the dam. This is a SAR image. So now we have talked about mostly about the geometrical aspects, means how the geometry is corrected from the level one product, and we are using the geolocation equations and the geocoding algorithms for correcting the geometrical distortions of the SAR. So what we have done in our last webinar, we have formed from the raw data to the SLC data, means the slant range product. So there we have used the signal processing technique. After that, we have lot of SAR and range Doppler equation. From that equations, we have done the data processing to convert the SAR slant range image to the proper ground range image or proper geocoded image using either the ellipsoid correction or the terrain correction. Okay, so that is all containing the geometrical part, means we are correcting the layover and foreshortening geometrically. Okay, so now we have known the SAR also have the speckle. So what are the post-processing techniques for removing that speckle? Now what is the speckle? The speckle occurs in the SAR image because it is a coherent device. So it is a coherent sensor. Due to its nature of the coherent sensor, there is the interference between the uh, there will be the interference between the SAR scatterers. So there will be the constructive interference and destructive interference. So that for the pixels, there will be the constructive interference, means where the scatterers have the same phase. Then we have the bright pixel, and for the pixels, there we have the destructive interference. We have the black pixels, means it is the form of the noise type of thing, means we are having the noise of black and white pixels. Okay, so that is a noise is called the speckle. So speckle is inherent to imaging of the distributed scatter because of SAR is a coherent imaging center. So this random bright and dark pixel appears as a noise in the image. So because SAR is a coherent sensor, then speckle is actually a physical phenomena. It is not called it as a noise, but its behavior is like that because it is forming a constructive and destructive interference, and it is forming a black and white pixels or bright or dark pixels. Then these bright and dark pixel will appear as a noise in the SAR images. So every coherent device like SAR, sonar, or ultrasound images also, we have this speckle type of thing. This speckle is multiplicative in nature because it is a function of the signal itself. Okay, so it is multiplicative in nature. So how the speckle will form? If the it is the constructive interference and it is the destructive interference, means if the scatterers are in same phase, then we have the bright pixels, then it will form a bright pixels, and if it is out of phase, then it will form a dark pixel. Then it will form a this variation degree of interference between the constructive and destructive interference. So these will appear as a noise in the image. So we have to build some of the speckle filters to remove this speckle noise. A good speckle filter demonstrates the following: speckle reduction in the uniform regions. Okay, means if we have the uniform regions like the lake, or we have the ocean or the ground, and like uniform regions, then we have to do the speckle reduction there. Means the speckle filter will do automatically good speckle reduction in the uniform regions, and it will preserve the edge, means if the buildings are there, and so there will be the edge preservation is there, and it should not have any artifacts, means the absence of the artifacts, and the radiometric preservation. We have the also the radiometry of the image should not change. So this is the basic characteristics of the good speckle filters. Means we have to remove the noise in the homogeneous region, means in the buildings proper edges. We don't have to blurry that things, means we have the proper edges in the images, and it will not introduce any artifacts, and radiometry should also be preserved. So basically, two types of speckle filters are there: non-adaptive and adaptive. So non-adaptives are those the parameters of whole image signals are considered. Means as a single image, we are considering the image and we are doing the filtering. do not take into consideration the local properties of the terrain backscatter. Means it will not do the locally anything. It will have a global filter. Okay, like FFT filter is the global filter. In the FFT filter, what we'll do, we have to do the frequency transform, and after doing the frequency transform, we have to find out the high frequency component. We have to cut the high frequency component and again do the inverse filtering and come to the our time domain. So this is called the FFT filter. Means for full image, we are doing the speckle filtering. Just we are going to the frequency domain, finding the high frequency component. High frequency component, why we are finding? Because the high frequency components are the noise. So that high frequency component we have to filter out. So what are the that we have to do the low pass filtering. So that low pass filtering we have to do, and that again we have to come back to our time domain by doing the inverse Fourier transform. So this is called the non-adaptive filters. Means we are doing the full filtering in the full image. Now, second type of filters are the adaptive filters. Okay, so what it is, the adaptive filters, now it will accommodate changes in the local properties of the terrain backscatter or local statistics it will do. Means it will gather the information from the SAR image. Means it will, from the locally, it will calculate the mu and sigma, means mean and sigma. Sigma is the standard deviation because the standard deviation represents the noise. So it will do the locally, means small kernels we have to form, means window operation it will do, and it will do the speckle reduction. So that are the adaptive, means it will do some of the kernel operation, means small kernels it will make, and we have to do within that kernel we have to do some operation, and we have to do the speckle reduction. So that are called the adaptive filters. The examples of the adaptive filters are the Lee, Kwan, and Gamma map. Okay, so how what is the leaf filter? Means for the leaf filter, what we have to do, we have to go to a particular pixel, and we have to find one of the kernel. Means kernel means one small window, either of 3 by 3 window or 5 by 5 window. For that particular window, we have to find the mean. Okay, and we have to find out the weights. Okay, so that weights. How to calculate the weights formula is given by this formulation. Okay, so by the formulation of mu and sigma. So mu is the that mean of a particular window, and this IC is the central. What is the central pixel mean? Okay, so this IC is the central pixel in the filter window. Okay, if we have the filter window, so IC is the that value, and mu is the mean value of the and that kernel value, and weights we have to calculate. That weight we have to calculate, and we have to apply this formula for that pixel. Okay, after using this formula, we can filter out the speckle noise. So this is the basic formula of for every type of filter. Means we have to find the weight differently. Means in the Lee filter, the weight will be find out with a different mathematical formulation. In the Kuan filter differently, and Gamma map differently. So basic difference is the calculation of the weights. Okay, so this is the Lee filter. So L, what is L here? L is the single look or multi look, because most of our SAR sensor will provide a single look complex image. Then single look means number of looks is how much. So number of look means in the azimuth direction how much looks are there. So basically for normal raw data processing, we have the single look images. So we are using L is equals to 1. In the multi-look processor means if we have the better images in terms of the radiometry, we will do the multi-looking in the azimuth direction. Means we have to use the synthetic aperture. We have to divide into 3 and 4 ways, and then we have to do the signal processing. So if the multi-look means if it is a 2-look image, 3-look image, then we have to use L differently. So most of the SAR sensor, it will give the single look image, and then we can use the L accordingly. And second is the Kuan filter. Kuan filter is also same. The resultant pixel can be derived with using this formula only, ICW plus mu W 1 minus W. And this is the W is the weight we are calculating. Okay, so this is the same formula, but the weights are different. Okay. In the gamma map filter, something different is there. In this filter, it will differentiate the pixel as homogeneous, strong target, or heterogeneous based on the window speckle index. Okay, so if the target is homogeneous, we have to find some lower limit and upper limit. If it is homogeneous, then we can find the pixel as the mean of the window. So we have to replace the center pixel as the mean of the window. If it is a target, then we have to replace with the IC, means center pixel. We have to replace in the center pixel, means if CI is lesser than the lower limit, or CI is greater than the upper limit, then we have to use this formula. If it is lies between this one, then we have to use this resultant formula like this one. Okay, so mu w, and there is L is there, and weight is there. So weight is given by this formula only. C U is the speckle index, and so this is also called the speckle index here. Cu and Ci is mu by sigma by mu. Okay. So this is the gamma map filter. So here you can see some of the differences. This is the original image Lee filter, Kuan filter, and this is the gamma map filter. We have applied different filters to the image. Okay, so another aspect is the SAR calibration. Why the SAR calibration is we have to do? Now, basically, the SAR images, what we are telling, like we have the phase is there, amplitude is there. Amplitude is given by the real image, real square plus imaginary square. So that it actually contains the DN value. Only the digital number is there. But we are talking as a backscatter energy. How much is the backscatter energy? So we have to convert that DN into the backscatter energy. So normally that backscatter energy is represented by the sigma naught. Okay, so that sigma naught converting to the sigma naught value, how to do? We have to do the SAR calibration. So what to do in the SAR calibration? In SAR calibration, the DN values of SAR is converted to actual backscatter values by estimating the calibration constant. The calibration constant is estimated through deploying the corner reflectors with known sigma naught. Okay, so how to do the calibration means we have to deploy some of the corner reflector in the field with the known RCS, means sigma naught. We have the prior information, and when satellite image pass to that corner reflector, then for that we have in the image we have some DN value. Okay, so then we can correlate that DN values with that backscatter values, and we can estimate the calibration constant. That calibration constant can be used to convert the DN into the backscatter value. Okay, so basically first we have to derive the beta naught. From beta naught we can derive the sigma naught, and then sigma naught can be derived, can be converted to the gamma naught product. So beta, what is the beta naught product? The radar brightness beta naught is derived from the image pixel values or DN values applying the calibration factor Ks. So this Ks is unknown. So we have to find this Ks. The formula is like beta naught is equals to Ks of DN square. So DN square is, and in the log scale, if we take the log, so in the dB is the means 10 dB is given by the 10 log 10 of beta, means this is the conversion in the dB scale. So in the dB scale, what is the formula? Beta dB is equals to, if dn square is there, then 20 log 10 dn plus k. Okay, ks is the log, ks is called the k. So this k we can find out. Okay, how to find out? We know the in image what is the dn and what is the beta naught in of actual corner reflector. Then we can derive this k also. Now, what is the sigma naught product? Sigma naught is actually the backscattered energy from a target influenced by the relative orientation of the illuminator resolution cell and the sensor. Okay, so the derivation of the sigma naught does require a detailed knowledge of the local incident angle. So if we are considering the local incidence angle in the means terrain in the consideration, then we have to find the sigma naught. Okay, so sigma naught are the basic product which we have to derive. So how the sigma naught is related? Sigma naught is equals to beta naught sine of theta of local incidence angle. This is the formula. Now beta naught from the this formula we can have. So for that, what we have the formula sigma naught dB is equal to beta naught dB plus tan log of sine of local incidence angle. Okay, from this we can derive this K. This we can put in this equation and we can derive. Now, if we have the better product, which is called the gamma naught product, it is normalized by the cosine of the local incidence angle. So, what is the um, gamma naught product? Gamma naught product is given by the sigma naught by cos of theta local incidence angle. So, that is the more precise product used by the scientific community. But most common product is the sigma naught product, which is used for the derivation of the calibration constant. So you can see this is the one of the image. So after the calibration, how the values are there from here -24 to 11 degree, 11 dB. So this is the calibrated product. And what are the ranges of the dBs of the sigma naught values? Like point target, it can go up to 50 dB. Okay, urban areas, it is go to 20 dB. 0 dB, -7 dB for the forest area. Vegetation means these means lower value it is having means it will appear as a dark hair, and it is higher value 50 20 it will appear as a bright pixels. So already in my first lecture I have told about how the target will look in different images. Means high backscatter value have the high backscatter energy. So point targets urban areas will appear as a bright tones, whereas vegetation and the water bodies will appear as a dark tones, water body due to the specular reflection. So this is a range of the different sigma naught values of different target in the images. So that's all in my lecture of data processing 2.